And now I would like to give the floor to Dr. Landin, to Professor Landin, to the colleague from Spain, to start with his presentation. Thank you very much for being here in this, I hope, interesting panel. And let's start with the first technical presentation. Thank you.
Hello, thank you for the kind introduction, Professor Ortiz. You can see my screen, right?
Of course, I can see your screen, and I can see your first slide. Everything is okay.
Okay, thanks a lot. Let's go. So, yeah, today I'm here my name is Santiago Muiños Landin, and I work for the AIMEN Technology Center in Spain, as has been said. And today I'm here to talk to you about some, well, I would say a specific AI technique that we are developing in the last years towards a more sustainable smart manufacturing, dealing with the design of products. First, some words about our center. This table of products is not updated. AIMEN is a technology center located in Spain, specifically in this region of Spain. It's a very nice one, which is called Galicia. Maybe you heard about it. We have a very delicious fish and seafood here. Our research center is, the main one is located in this region in Pontevedra, but we have different locations also along the Spanish geography. And our center is divided in different areas of research. The one that I belong to is a smart systems, a smart manufacturing unit, where I lead the artificial intelligence and data analytic department. But we also have strong research activities on laser-based manufacturing, advanced materials, and also environmental technologies. We have mainly our frameworks for research deployed a lot of different European projects on different topics from ICT to factories of the future. This is from the old program was called Horizon 2020. We are now on a different program. But the different projects are with applications from real manufacturing and additive manufacturing, particularly the strongest in AIMEN, but also welding systems, advanced materials, and also environmental science. For instance, we have different projects on water quality management, also projects on health. So the spectrum of applications that we have is quite broad. But today I'm here to talk about some part of our developments in artificial intelligence. And dealing with artificial intelligence, we work on the typical domains. For instance, the development of our own AI models, for instance, for the identification of key parts within a manufacturing system. For instance, you can see here how through the deployment of convolutional neural networks, we can do semantic segmentation and identify, for instance, there's wire in a welding system, or we can also identify the torch or the melt pool here and track in real time the position of these items here in order to quantify what is the influence of the variation of these of the position of these elements in the manufacturing process, and what is the impact of these fluctuations on the performance of the system through the analysis of MT data, for instance, after the process takes place. We also have predictive models, deployment, concatenated with convolutional networks so that we can identify pores in a welding system like those here, and we can also concatenate this identification with data coming from electrical signals in order to predict when do we have these kind of patterns and avoid them in real time. We also identify through computer vision systems different parts of a body so that we can define communication channels between a robot and a person collaborative environment so that the operator can establish some kind of pose in order to give some instructions to the robot and do that in real time. So this is quite state-of-the-art technologies that we deploy in different manufacturing systems at AIMEN. And also a very important part of our research deals with the optimization of the data structure. Here I have an an example of the integrated project, which was finished, when we addressed the definition of the whole data frame, the data workflow, let's say, from manufacturing, additive manufacturing process of metallic parts, from the design to the certification of the part, passing through all the different phases. I mean, an additive manufacturing process is complex from the design, given that you have to design the piece that will be perfectly manufactured depending on the additive manufacturing process that you use. At the end, you have path planning. You can perform simulations that provides you some hints about if you are choosing the right paths for the manufacturing and so on and so forth. So at the end, you have a humongous amount of data that needs to be optimized on its construction in order to enhance the chances that you might have later to exploit this data to optimize different points of that manufacturing workflow. Let's say, for instance, we defined for additive manufacturing different levels of complexity of the data coming from the software itself that you use in order to address the different points of the manufacturing chain to the different operations, for instance, the simulation, path planning, metrology, entity, and so on and so forth. And then different layer of complexity, which is how to handle the raw data, the raw data, for instance, for the monitoring process from the entity itself, different tomography data or X-ray data that you might have from piece, so that at the end you have a well-structured data set that you can exploit through artificial intelligence, for instance, to optimize the design as a function of how good that design performs in the manufacturing of itself, based on data coming from the monitoring process, so that you can feed your design algorithm based on what is the outcome of the processing data that you can evaluate, taking a look at the process data or the entity data. So this was quite hardcore for us, and we started to work here actually with the idea of applying artificial intelligence to optimize the design of a product. And intuitively, what was natural for us was the application of genetic models, for instance, for the deployment of AI to the design of a product. If you type in on the internet genetic models, and you will probably have some inputs of generative adversarial networks, GANs for short, that essentially are to neural networks that compete with each other, then they evolve in different, more complex and more accurate models like the diffusion models. But these GANs are quite intuitive from the point of view that you have two different networks competing with each other. You have a generator network that tries to take some noisy data and to manipulate it somehow to make it look like real data that you have from a data set. And another neural network tries to classify the outcome of this generator as a real or fake data, so that the discriminator tries to see if the data generated by the generator looks like the one that you have in your dataset. And once the performance of the generator is good enough, then it fools the discriminator, and then you have generated data which is synthetic and is essentially quite similar to the real data. And this, if you type GANs on Google, then you will have a lot of faces of pictures of faces, pictures of animals, pictures of fruits, of digits, and a lot of pictures. So we started to work with these genetic models for the generation of pictures. And one quite intuitive application that we found was the generation of synthetic data for defect detection based on image, when we had not enough data to train our network to perform a given performance. For instance, it happens from time to time that you have different typologies of a defect. For instance, here in this image, you can see a crack. This is an image of a crack of a metallic part in the manufacturing of an automotive part, a part of a car. And you can see these cracks like that if you put these pieces under a bath with magnetic nanoparticles. This is a quite standard technique in order to detect cracks, you put the metallic part in a bus with these magnetic nanoparticles, and these magnetic nanoparticles, if you magnetize a part, they tend to accumulate where you have an homogeneity on the magnetic field here, so that they accumulate on this region. And if you put some UV light over these peaks after you put the piece in a bag, then they shine and they look like something like this, so that you can detect somehow these cracks by this accumulation. And it happens from time to time that you don't have enough data to train properly neural network to detect them. But using these generative adversarial networks, we manage to generate some synthetic pictures like those that you can see here. Those are real cracks, and those are synthetically generated cracks that we use to train our detection model and improve the performance of quality control system. So we thought, okay, these generative models work quite well in order to create images, and maybe it could be used, this technology could be used to create also designs of product. And we had a nice environment to start working with that. And what we thought is, okay, we have a nice environment, as I will show you later, to work with the application of genetic models for the design of the product, but what do we have in order to evaluate the performance of a system that provides some design of a product? If you think about what a design is, then you have different phases along the design process, let's say. In order to understand what the product is, you need some kind of requirements that the product must fulfill. Then you have to prototype this product in order to address those requirements. And then you have to test if these prototypes satisfy those requirements and make the production of that product happen, right? But if we want to use artificial intelligence to generate a product here, how can we evaluate properly, or what are the indicators that could provide us some feedback about how good the design is? And for that, we found that sustainability indicators might be a nice point. For instance, what kind of materials do we use on that design? What is the recyclability of that product, or the recyclability of the materials used on that product? And so on and so forth. So those are indicators that can be quantified and that can give us some feedback about the goodness or the quality of the design, which is quite usually a very tricky thing to quantify those things. And as I said, the nice framework that we had in order to start working with generative AI for the product design was the INEDIT project, a European project that also recently finished last month. And on this project, we defined what is called a social manufacturing framework. In this social manufacturing framework, you have a manufacturing chain that is divided in different users of the manufacturing framework that provides different services. For instance, you can have a logistic partner in your social manufacturing framework. You can have somebody that addresses the recyclability of the product, somebody that makes a material supply, so on and so forth. And the role that we addressed here was the design of the product. Focus this project on the design of furniture. And we exploited the potential of artificial intelligence to enhance the capabilities of a user of this social manufacturing framework. And we enhance the design capabilities through the deployment of artificial intelligence, more specifically through the deployment of generative models. The was to deploy a particular architecture of neural networks, which is called a variational encoder, that essentially captures the essence of a design. In this case, you can see here this chair. And in the same way that you define what is the position of a point in the space by decomposing the position in three different dimensions, X, Y, and Z, then the variational encoder does more or less the same, but in hundreds of dimensions. And once you encode this information in this latent space, so-called, then you can introduce some variations on that reduced space, so that you can produce variations of that product and decode this variated product and have a different design of your initial product. And this essentially provided a tool for the deployment of hundreds of different models of furniture items like chairs, tables, sofas, beds, and whatever. And in a question of some seconds, you can have as many designs as you want. And we concatenated this with the additive manufacturing of these kind of models, so that you go to your system, you don't know exactly how to design a chair, so that you use your AI tool. It provides you some designs, and you choose the one that performs better for your taste, and you evaluate the manufacturability as well as the manufacturing of this piece, and you can actually send it to print. You can even evaluate how does it look in your environment through the application of augmented reality technologies. And you can even design through AI also different patterns on the surface to make the item look like something which is not real. For instance, we have here a plastic chair which is printed with a texture that makes your chair looks like made of wood. And more importantly, you can also, before sending into print, sending into production, you can have some evaluation of the environmental impact of that production, because you can have some quantification of how much energy will be invested in the production of that chair, what kind of materials you have available to product that chair, and what is the environmental impact of those materials, if they are recycled or they can be recycled, how good the recycle process might be, and so on and so forth. So we include the capabilities of enhancement design capabilities to the users, and we introduce the sustainability indicators on the production of this kind of items by the introduction also of the materials assessment, let's say. And given that we started with this part of the materials, we had another environment to work on the performance of a material and how to design a material to enhance its performance, and how to design a material to enhance somehow the sustainability indicators that one can define. And this was done in the context of this project, also an European project still ongoing, which is called Achieve. In Achieve, we addressed the definition of AI tool for the design of high entropy alloys. Specifically, high entropy alloys are, well, if you type on Google, you will see that these alloys perform extremely well at high temperatures and high pressure, and that was the main scope of the project, to develop different materials, novel materials for exigent or harsh conditions. And if you have the capabilities of designing this material in order to enhance its performance, you can also address at the same time the sustainability of the product per se, because you address the material that you will use for the production of that material. But you can also evaluate indirectly the performance of that material, because you might have some indicators of how good is the performance of that material for its application. For instance, how biocompatible the material might be at the end, or what will be the hardness or the thermal conductivity of that material, so on and so forth. And actually, the deployment of AI for this problem is quite natural, because if you think about the complexity of developing a material, you can think about the different combinations of the elements on the periodic table. You will see that the amount of combination is huge. And if you also consider the different spatial configurations of the elements of the atoms along the lattice, and the number of combinations becomes even higher. So we applied essentially the same kind of architecture, but in a different way and with a different data set as in the Inherit project. We use a GAN, a generative adversarial network, trained with data sets from literature and from experiments, in order to provide candidate materials through a discriminator network that was evaluating how manufacturable that material was in terms of different parameters from material science. and how real the sample is. And one key issue is to define which one is the best outcome of that kind of network. For that, we inserted our genetic approach into our reinforcement learning framework in order to make it interact through computer simulations, through alpha simulations, that essentially provides us some hints about what is the final thermoconductivity, the hardness, jump modulus, whatever, of this candidate material provided by the GAN, so that we have some indicators about the goodness of that material, and we can also filter these materials from sustainable indicators, like for instance, if there are some toxic elements on the alloy, if they are too expensive, if they are not available in the region at that moment, so on and so forth. So you have enhanced capabilities in order to choose what material to develop for that purpose that you want right now. And actually, we have some experimental data that supports our tool. If you take a look at the production with the additive manufacturing process suggested in the CHIEF project, you can see that if an expert takes a look at the literature and provides a candidate material, you can see, well, maybe you are not used to see this kind of pictures, but this is a sample of high entropy alloy additive manufactured that presents a lot of cracks. And if you take a look at this one, which was with the alloy provided by our AI tool, then you have a better performance, better structure, and so on and so forth. And that's those are the two cases that I wanted to comment with you today. We also are working right now with the assessment, not just the performance, but also the assessment of how to address the disassembly of a project, of a product, and how to include this kind of indicator in the design phase of the algorithms within the couple project, which is the month 6 right now, so it's almost starting. And I guess I'm a bit out of time, so I just leave the conclusions here, just wanted to let you know, just to open maybe some questions. And I'm open right now for discussion, and I want to thank you for your attention and highlight that we are hiring right now, so feel free to try and discuss if you are looking for a position on AI. Thanks a lot for your attention.
Okay, thank you, Professor Landin, for this very interesting presentation. And now I think that we have time for a couple of questions from the audience, which can be transferred to Professor Landin. Please, is there any questions from the audience? If it is not the case, or maybe someone would like to take some time to think. Okay, I have a question. I have a question, dear colleague, regarding, because your presentation was very interesting and was very much about the design of the use of artificial intelligence in the design of products and processes and so forth. I have a question. Is it possible, or have you any idea on how this, let's say in quotation marks, generative AI could support computer-aided process planning?
Well, you mean process planning from the aspect of how to organize different tasks?
Exactly. Exactly. I mean, you know, in the you had a very nice slide there with the number of molecules and a huge number of alternatives to combine these molecules. Some 10 or I think in 100 exactly 10 or in 100 of 70. It's a huge number. Impossible to work it out in physical terms. So my question is that in case of process planning, especially in big factories, in big systems, with large systems, we have hundreds, even millions, billions of combinations of different processes and parts, and we try to find somehow, let's say, a good solution among these possible similar families of parts and processes in order to proceed in a fast way in a new design.
Oh, the new design of the whole chain.
Artificial intelligence,
maybe,
especially. Yeah.
I mean, maybe, but it's hard for me right now to think about the nature of the data that you will need, because at the end you will need to have clearly quantified the different parts. I mean, what motivated the different parts and so on and so forth, and how to evaluate those parts. That could be done at the end at the evaluation, but it depends on the level of detailization of the parts you have. Maybe yes, I would more intuitively. I would think more on evolutionary algorithm for a task like that to design the paths. But honestly, I cannot say yes or not. What I can say is that that task for me is more natural for the evolutionary dynamics domain rather than this one. Maybe yes, addressing it not from this perspective of generative networks, but from the perspective of diffusion models, where you essentially take as inspiration from diffusion processes in nature, and it's more similar to the evolutionary dynamics, because at the end you are introducing the stochastic fluctuations on your system, and for me it would be more natural. It's a hard question, because but I would think about that, and maybe in the following discussion, if I come to an idea, I will let you know.
Okay, maybe you submit a paper on this issue, on this concept in the ongoing
maybe
we have opened.
Actually, I'm writing one perspective one, so maybe it could be a nice approach. Yeah, I will put you as a comment.
The second question, if someone from the audience have no question to make, how do you think that quantum computing could influence the applications of artificial intelligence in product and process design? Well, quantum computing is at the portals, you know.
Yes, absolutely. Yeah, I think I mean, the impact will be huge in terms of speed of the designs. For instance, for the design of these furniture pieces, it takes lots of computing power for the design of tens or of products, and it's not a really complex situation. You have just a distribution of boxes in not super high resolution. But I guess that with quantum computing, you will manage to go in extremely high resolution design of the objects in a very fast fashion. So I will expect the application of quantum computing on this domain to speed up the amount of designs and capabilities in terms of complexity. It still depends. I mean, a bottleneck is the availability of data sets to have initial designs. In some cases, that's, as I say, a main bottleneck that we have. The companies don't have thousands of designs of a machine that can be improved, for instance, through these techniques. They have, I don't know, 10, 20 designs. So that's the main bottleneck right now. But yeah, just going straight to the question, I guess the main impact will be in terms of precision and speed of the provision of designs.
Okay, thank you very much for the interesting presentation and the even more interesting discussion. We expect to see one of your papers to be submitted to the journal. And please stop sharing your screen.
Right now. I already stopped.
To start sharing my screen and start with my presentation here.
Thank you.